The objective today is to analyze the importance of registers to a CPU. So in terms of a table of contents, I'm going to tell you what they are, what registers are. Then we're going to talk about the difference between processors. And that's kind of funny to say because it's like saying, what's the difference between a steak and a cow? You know, because a steak is inside of a cow, a register is inside of a processor. But anyways, after that, I'll go ahead and just give you a straight up definition, see if that helps. The fourth thing we'll do is give you an opportunity of additional research. So I'm calling this section of my videos an opportunity for advancement. Maybe plant the seed of curiosity in you right there. After that, we're going to talk about what it means to have a locality of reference. Then we'll wrap up the lesson with talking about the number of registers you can find in different types of CPUs, and finally the laws of nature and how they are ultimately the reason we are having to use registers in our computers. So while doing some research for this lesson, one website called a register a data holding place. Sort of makes me think of cattle, like how cattle are in this holding cell right before they are slaughtered. To take this analogy and compare it to a computer and the data in that sense, data such as actual data or instructions or addresses, these things, these ones and zeros, are just sitting there waiting to be executed. Get it? Executed like slaughtered? But in processor terms, this has a totally different meaning. And to take that analogy a little bit further, there are many holding cells in a computer. A register is the one closest to the actual processing part of the CPU. That processing part is known as the arithmetic logic unit. More on that very important thing later, but that little thing right there is probably where the term processing is coming from. And I just like the word cells because when I'm thinking of data, these ones and zeros, it's nice to think of these ones and zeros in little boxes. But let me give you a more professional definition. In computer architecture, a processor register is a quickly accessible location available to a computer's central processing unit. In another lesson I have coming up for you, I'm going to have you differentiate the speed of computers using Hertz appropriately. And in this lesson, I'm going to try to make the big point that the secret of computers is not that they are complex, but rather they are very fast. So to go back to this definition, a register is a quickly accessible location. That is the key to why registers are important. So let me give you some visuals here to digest. Here's a picture of a CPU, a processor, a microprocessor, 100 words that are different to mean the exact same thing. Those who have had me as a teacher before know this is a complaint of mine about the field of computer science. But this rectangle chip, maybe it's a square if we measured these sides and found out they're the exact same. But regardless, this chip here has an area that is where data is stored, and this area is called the registers, and even each one has its own fancy name. And then you'll have another part of the chip that is in charge of decoding. I'll have that in a whole separate lesson, and of course the ALU would be another separate lesson, but just want to give your mind some visuals here so that when I say the word register, you have something in real life to think about. Now, those who know anything about computers know this picture is a real horrible situation. You don't want to be that guy. Somebody has taken thermal paste and put that on the pins. We're right here where my mouse is. This is the connectors. The pins are down here. Why did they do this? They just don't know what they're doing. My students in class like to use this word cringe, and that picture right there is definitely cringe. This right here is a better view of what I'm talking about. You have a CPU, and somewhere amongst all this metal is an area. The area might not look too different from the other parts of the chip, but this is a register area. And there are many forms a chip can come in, not just this. For the students physically in my class, make sure you ask to see one of these. I have them on my desk. But a chip can also look like this. This is also a processor. This is the 8008 processor. And when we took a microscopic look at it, we can see that the registers are bundled over here in this corner. And then if you go down here and count each one of these pins, there's 8 on each side. I made the connection that right here where you see these little black dots, probably where someone took a Sharpie marker and just marked them, those are the entry points for the electricity. And once they enter the chip, all kinds of magical things happen. So if you're a student in this class interested in cybersecurity, I'm going to try to just encourage you to go forth and do some additional research with this fact. So the fact is, some registers have specific hardware functions and may be read-only or write-only. I wonder what that could mean and what the implications of that is. But the big fact that should seed some curiosity in you is the fact that there's modern high-performance CPUs that have duplicates of architectural registers, and they have these duplicates in order to improve performance. The way they improve performance is through something called register renaming. Another strategy is to use parallel processing. But the thing most related to cybersecurity here is speculative execution. The fact that the architectural designers of these chips created this ability to speculate on what's to be executed next has given rise to this Spectre and Meltdown vulnerability. Now, modern x86 design acquired these techniques around 1995, so this has been around for a while, and this occurred with the releases of the Pentium Pro, the Cyrix 686, the NX 586, and the AMD K5. This is a long list of processor names. And though that may be a little overwhelming, like all these processors have different names, all of them will have some sort of registers working for them, so at least that basic building block is the same. And if you think it's hard to remember the names of all the different processors out there, imagine trying to learn the names of all the registers in one of those processors. But more on that slide later. For now, I want to talk about a common property of computer programs known as the locality of reference. This is a reference to accessing the same values repeatedly and holding frequently used values in registers to improve performance. So maybe I'm working on a project like adding the number 7 to many other numbers. I could just hold 7 in a register, and then every time I get one of those other numbers, that's the concept of locality of reference. I'm going to continue to refer to that one number, so why change it every time? Why don't I go ahead and just keep it the same? Now that might be an oversimplified example, but here in this class, I want you to make inferences. So the challenging part of this think right share is, can you infer a situation in which a value in a program is used often? Maybe we're talking a game or a text editor. What types of values may be referred to often? And if you haven't seen this video on the Scott CPU yet, I highly suggest it. I think they just give you a wonderful visual in terms of what's going on when you're using a computer. Like right here is the RAM, this is the processor, so there's registers in there, right? The lines coming out here is what's called the address bus. You have your two very important wires here called a set and an enable, basically the ability to read and write, and then on this side you have the actual data. So this little cyclical concept will come in handy when you're looking at what value is placed in certain registers. So say, for example, you have one register where you're going to put the value that's at a particular address, maybe this gray address here. So this address will enable us to read this data. That's a little complicated. I'll go more into that later. But let me give you more speed facts. And I hope you're picking up on this pattern here. The objective is analyzing the importance of registers to a CPU, and somehow I just keep mentioning speed. So your speed fact of the day is allocating frequently used variables to registers can be critical to a program's performance. My coders in the room may have just perked up at the word variables. This register allocation is performed either by a compiler in the code generation phase, or it's going to be established manually by someone who likes assembly. My favorite programming languages to look at are the assembly ones, though I prefer the Intel syntax over the AT&T. And if you want to hear more people like me nerd out about this stuff, here is a terrific discussion on how many registers are in these types of processors. You got the 8086 and the 8088. The person asking this question, Fahid Udin, it looks like. This person says, I took computer architecture course and I understood that processor has 32 registers, each of 32-bit. So great way to start. Like, this is a person, you can go to college and take our computer architecture courses. I found a good one on YouTube from Carnegie Mellon that you might want to check out. But this first answer is a terrific one to just start wrapping your mind around how registers work. The person here is clarifying that in these types of processors, the 8086 and the 8088, these are only 16-bit processors. For you in my class, this means we are talking about a baby processor. This is like the olden days. In my lab, we have 64-bit processors you're working with. But they go on to give some really good information about this concept called general purpose registers. So here they all are. Later on down, you'll hear about the special purpose registers and then flag registers with lots of details. Down here, a little more condensed form of the same information. And I just like Stack Exchange. It's somewhere you should probably go to often if you want to make a future of this. And also in your future, make sure you're asking questions like me. I just came up with this one randomly, and I realized as your teacher I didn't have the answer, so I went and found it. And it's a little more complex than that one website I showed you, because I discovered that it just totally depends on the architecture. Whatever architecture we're looking at would determine the number of registers. So an x86 has 8, ARM 32-bit ones and x86 64 ones have 16 registers. But the beefiest one of all that I found is something called an IA64, and this has 128 registers. So with that said, here's this slide again I showed you earlier. I wanted to talk a little bit about the Intel Core i7 and i5 because most of my students are working on i5 processors right now. You can go to your little Cortana tab on the top here and type in about, and then click about your PC to see how many gigahertz you're working at, along with how much RAM you have. And the third number you might notice is whether it's a 64 or 32-bit system. Here in the lab, we're looking at a 64-bit system. So that means how many registers do you have in the computer you're looking at right now? You're likely looking at 16 of them. And then if you think this is confusing, wait till you look at a GPU. GPUs typically have even more registers than CPUs. So just for the fun of it, go ahead and look at our chart here and choose a favorite register. I know a lot of people who would say the EAX register is their favorite. An extra credit if you can tell me why you think that is. But let's focus here and wrap up the lesson. There are many architectures out there that have chosen a variety of registers, and in my mind, I sort of think about building a house. So the number of rooms you have will depend on your needs. If you're a single person, you don't even need more than one room. Your kitchen, living room, the place you sleep can all be in just one room. Maybe if you have guests, you'll want your bathroom to have a door. But see how it all depends on your needs? Same with computers. Different types of computers used for different purposes will need a different number of registers. And if you click on that Wikipedia article link, here are a variety of architectures. Here's the number of registers. And here's some notes on those. And for the best named architecture, I think the first one may win. I mean, what's cooler than having a Hobbit architecture? But Professor H's favorite is actually going to be this one, the 6502. Fans of the movie Terminator might recognize that. And fans of Futurama may as well, because that is the processor in Bender's head. Not to mention, learning that assembly language is actually pretty easy. So at this point, many of you might be wondering, why don't we just go directly to the hard drive to get the memory, to get the ones and zeros that we need? Well, the answer is pretty simple: speed. Just like that quote I had near the beginning of the lesson here, the secret of computers is not that they are complex, but their speed. So the physical laws of our universe make us create the systems that we do. And like any good teenager, we humans are finding a way around those laws to get what we want. We want fast computers. If you look at this nice little chart I found, basically the physical makeup of registers allow us to access those ones and zeros very, very fast. But they're not good for long-term storage. I can't put my movie on a bunch of registers and have them sit by the processor ready for me to go. No, I want something like a SSD or a hard disk to store my movie, and I don't need to keep pumping these things with electricity to keep those bits stable. RAM right here is a nice in-between for us, and so is this CPU cache. But even look at the magnitude of difference right here from a CPU cache. The cache can access speeds up to 100 gigabits a second, Registers blow that out of the water with 1,000 gigabits. If you are chomping at the bit to know more about this, I suggest you go to YouTube and search for the Crash Course Computer Science Arithmetic Logic Unit video. Here's just one picture from it. It's a really great explanation of how all this works. So here's the end of the lesson. I just want you to tell me, how important is a register to a CPU? Good luck and don't give up.